This week's lecture will be based on information from Chapter 20 in your textbook. We'll be looking at the cardiovascular system and specifically looking at the heart. So we'll do a review of the anatomy of the heart that you would have done in your first semester, and then also look at a little more physiology as it pertains to functioning of the heart. This slide is a simplified image illustrating the circulatory or cardiovascular system in the body. Cardiovascular system is basically comprised of the heart and the associated blood vessels, the arteries, the capillaries, and the veins. And one of the major functions of the cardiovascular system is to supply oxygen and nutrients to the tissues and the cells in the body, and also to provide a vehicle for transporting the waste products of cellular metabolism, including the carbon dioxide, back up into the lungs so that we can get rid of the carbon dioxide when we exhale. So the heart is basically two pumps in one. You have the right side of the heart and the left side of the heart. The right side of the heart will pump deoxygenated blood, or blood that's not containing oxygen, up into the lungs via the pulmonary circulation, and that's where the blood then will pick up the oxygen and release the carbon dioxide, and then the oxygenated blood will come back down from the lungs to enter into the left side of the heart, and then the left side of the heart will then pump that blood into the systemic circulation so that the tissues and the cells throughout the body get the nutrients and oxygen that they require. The veins then will return the blood back to the right side of the heart, and again this will be deoxygenated blood, but in the tissues this venous blood is also picking up the carbon dioxide that's being formed due to cellular metabolism and returning it to the right side of the heart. The right side of the heart again will pump that deoxygenated blood into the lungs and to continue with the gas exchange that occurs in the lungs. Looking at some of the major functions of the heart, first of all, the ability of the heart to generate blood pressure. So the stronger the heart contracts, the more blood pressure it's going to create in the arteries in the body. It also functions in routing blood. So again, the right side of the heart will pump blood to the pulmonary circulation, to the lungs, and the left side of the heart will pump to the systemic circulation, to the rest of the body. The anatomy of the heart will also ensure that blood only flows in one direction. So we remember that we have valves in the heart between the different chambers and the major blood vessels leaving the heart, so that blood can only flow in one direction and not backwards. And also the heart has a function in regulating the supply of blood. So when you are, for example, exercising, your tissues, your muscles are going to require more oxygen, more nutrients, so the heart rate will increase and the strength of contraction will increase as well. So it can regulate blood supply to the tissues that require it, depending on demand. Remember the location of the heart within the body. It lies in the mediastinum, in the thoracic cavity, so it lies between the two lungs. It's superior to the diaphragm, inferior to the first rib. It would be posterior to the sternum and anterior to the vertebral column. And it's basically the size of your closed fist. The heart lies within a bag-like structure called the pericardium. You have two major components to the pericardium. You have the fibrous pericardium and you have the serous pericardium. The fibrous pericardium is the outer sac. That's a very tough fibrous layer, and it helps to anchor the heart to the diaphragm and to also prevent the heart from overstretching or over-distending when it's being filled with blood. The serous pericardium is divided up into two parts, the parietal pericardium and the visceral pericardium. The visceral pericardium is also known as the epicardium, and that's the layer that is the outermost layer of the heart, or the part of the pericardium that will be in contact with the heart itself. Viscera means organ, so visceral pericardium means that part of the pericardium that is attached to the viscera or the heart. Between the parietal and visceral pericardium there's a space, there's a pericardial cavity, and this is filled with pericardial fluid, so it helps to prevent friction with the moving of the heart. It allows a more frictionless action as the heart is moving, pumping, and becoming distended, and then contracting and distended, etc. And pericarditis, just as an aside, is if there's a condition where the fluid within the pericardial cavity becomes infected. This results in an inflammation or infection of the pericardial fluid known as pericarditis. If we look at a section of the heart wall, we see that there are three layers. The outermost layer is known as the epicardium, which we already discussed, is the same as the visceral pericardium. And this is where the blood vessels are located that will supply blood and oxygen or oxygen and nutrients to the myocardium. The myocardium is the cardiac muscle, so that's the muscular component of the heart wall. And then the endocardium is the smooth inner surface of the chambers of the heart, and it's smooth to try to prevent or minimize the friction of when blood is moving through these chambers. And the endocardium is also continuous with the inner lining of the blood vessels that will be leaving the heart and entering the heart as well. Looking at the external anatomy of the heart, we'll just do a brief review again. Remember that the deoxygenated blood is returning to the right side of the heart, and so blood from the upper half of the body will be returned to the right side of the heart via the superior vena cava, and blood from the lower half of the body will be returned to the right side of the heart by the inferior vena cava, and this blood will then enter into the right atrium. The right atrium will then empty that blood into the right ventricle. And remember that the right ventricle, when it pumps, will pump the blood up into the pulmonary circulation. In this case, the pulmonary trunk, which will then divide into the left and right pulmonary arteries, which will then enter into the lungs, left and right lungs. And this is where this deoxygenated blood will be releasing its carbon dioxide and picking up the oxygen within the lungs. And then once the oxygenated blood leaves the lungs, it's going to come back via the pulmonary veins from the left and right lungs. The pulmonary veins will bring the oxygenated blood back into the left atrium. And then the left atrium will pump that blood or empty that blood into the left ventricle. And the left ventricle will then pump that oxygenated blood into the systemic circulation through the aorta and to the rest of the tissues and organs in the body. Because the right side of the heart, remember, is only pumping into the lungs a very short distance, the myocardium of the right ventricle tends to be thinner than the muscular wall of the left ventricle. The left ventricle is pumping to the entire body, so its myocardium, the muscle layer of its heart wall, is very thick relative to the right side. And both atrium, right and left atrium, are thin-walled structures because they're not really pumping blood any distance at all. Basically, most of the blood will just passively leave the right atrium into the right ventricle and passively leave the left atrium into the left ventricle. So these atria are thin-walled chambers. Looking at the external anatomy of the heart, again, but from the posterior point of view, and I just wanted to point out, again, you likely learned this before, but just to emphasize that there's an anomaly in the naming of the pulmonary veins and arteries associated with the heart. Typically, we associate arteries with carrying oxygenated blood and veins with carrying deoxygenated blood. But more accurately, arteries are defined as blood vessels that are taking blood away from the heart in the body, and veins bring blood back to the heart. So in the case of the pulmonary arteries, we see these pulmonary arteries here, right and left pulmonary arteries. So when the right ventricle pumps deoxygenated blood away from the heart and to the lungs, these are this blood is traveling in the right and left pulmonary arteries. So even though they're called arteries, they're carrying deoxygenated blood to the lungs. And then when that blood is oxygenated in the lungs, it's going to return back to the heart. So because this is blood that's returning to the heart, it's in the right and left pulmonary veins. Even though that it is oxygenated blood, it is still returning within the pulmonary veins. Looking at the internal anatomy of the heart, we'll point out the four chambers again. So here's the right atrium. We have three openings in the right atrium, one from the superior vena cava, one from the inferior vena cava, and one from the coronary sinus. The coronary sinus is bringing blood back from the heart tissue that's being supplied by the coronary arteries. Blood from the right atrium is then shunted into the right ventricle through the right atrioventricular valve, which is also known as the tricuspid valve. The right ventricle will then pump that blood, this deoxygenated blood, into the pulmonary trunk. Pulmonary trunk divides into the left and right pulmonary arteries that will then go into the right and left lungs. And in the lungs, this deoxygenated blood gives up its carbon dioxide and then receives oxygen. And now the oxygenated blood will return from the lungs back to the left atrium through the left and right pulmonary veins. And from the left atrium, that blood will then be shunted into the left ventricle through the left atrioventricular valve, also known as the mitral valve or the bicuspid valve. So bicuspid because this valve has two cusps or two leaflets. And then from the left ventricle, notice also that the left ventricle is a very thick-walled, very thick muscle chamber, because now this blood is being pumped from the left ventricle into the aorta and to the systemic circulation to the rest of the body. Looking at the atrioventricular valves again, so we have two atrioventricular valves. We have the right tricuspid valve here, and we have the left bicuspid or mitral valve. So these are valves that separate the atria and the ventricles. And remember that these cusps of these valves are connected to the papillary muscles that are part of the walls of the ventricles, and by these structures called the chordae tenoni, these strings. And so when the ventricles contract, the blood that is inside the ventricles is increasing in pressure, and it shuts these valves. And part of the function of the papillary muscles is to prevent the cusps of the valves being forced back into the atria because of the buildup of pressure within the ventricles when the ventricles are contracting. So the papillary muscles contracting as well when the ventricles contract, so that helps to prevent these valve leaflets from being forced back into the atria. Two other structures in the fetal heart, the last slide made reference in the text, but I didn't talk about it in the last slide, is the ductus arteriosus and the foramen ovale. So remember that in the fetal heart, in the wall between the atria, the interatrial septum, there is a hole in the fetal heart. It's called the foramen ovale, and this allows blood from the right atrium to be shunted into the left atrium without having to go into the right ventricle, because in the fetal heart there's no real purpose to the right ventricle pumping blood into the pulmonary trunk because the lungs are not functioning yet. So we have a mixing in the fetal heart of a mixing of oxygenated and deoxygenated blood, and so the foramen ovale will serve that purpose between the atria. And then also whatever blood is pumped from the right ventricle up into the pulmonary trunk will be shunted through another opening called the ductus arteriosus into the aorta. Because once again, whatever blood is being pumped into the pulmonary trunk, there's no need for it to go to the lungs because the lungs are not functioning. So the fetal heart, the fetus itself gets its oxygenated blood, or its blood is being oxygenated from the maternal circulation. So it doesn't rely on its lungs when it's still in utero. So this is called the ductus arteriosus, and then shortly after birth, this will close off and become the ligamentum arteriosum. And the foramen ovale here, the hole between the two atria, would also close off to just create a depression in the interatrial wall, or the interatrial septum, that's known as the foramen ovalis. The two other valves that we have in the heart are the aortic and pulmonary semilunar valves. And again, these valves will prevent the backflow of blood. So if we were to look here at the left ventricle, so this is the aortic semilunar valve. So when the left ventricle is relaxed, blood is coming in from the left atria into the left ventricle through the bicuspid valve. And as well, the blood that has been pumped in the last cycle up into the aorta, because this pressure now is decreased in the left ventricle, blood is allowed to come back down the aorta, and it fills these cusps or cups of the semilunar valve, and that causes this valve to close. So this prevents blood from the aorta returning right back into the left ventricle. When the left ventricle now is going to start contracting for its next cycle, so as it's contracting, the pressure is building inside the blood pressure is building inside of the left ventricle. These papillary muscles contract, and the pressure is closing the bicuspid valve. And but once enough pressure is created, it's going to force the aortic semilunar valves to open, and blood is able to leave the left ventricle and go up into the aorta. And again, once the ventricle stops contracting, blood is able to regurgitate back down the aorta, fills up the cups here, and the semilunar valve will then close. So this is the same in the on the right side of the heart. So we have the pulmonary semilunar valve that is going to be between the right ventricle and the pulmonary trunk, and it serves the same purpose and has the same mechanism of action as the aortic semilunar valve that we just talked about here. Recall that the heart itself also has to have a blood supply, and so this blood supply comes from the coronary arteries. So the blood that's being pumped into the aorta from the left ventricle, one of the first branches that come off the aorta are the coronary arteries, left and right coronary arteries, that will supply the heart muscle itself. A myocardial infarction or heart attack occurs when one of these branches of the coronary arteries gets blocked, either by a clot or a thrombus that develops locally in that blood vessel, or possibly from an embolus if there's a clot that originates somewhere else in the body that makes its way up into the coronary arteries and eventually is able to block off one of those small blood vessels. It stops now the oxygen and nutrients from going past that point, and whatever muscle is being supplied by that branch of the coronary artery will die. And that's basically what a heart attack or a myocardial infarction is. Of interest, we know that muscles throughout the body, if we are stressing them with regular exercise, that the muscles will, as they get larger, will create more blood vessels. And we know the same thing happens in the heart, that if there are little blockages, for example, that may be happening within the heart, or you're getting some clogging of these arteries, if you continue to exercise and stress the heart muscle, the heart will develop new blood vessels to try to bypass those blood vessels that are getting progressively blocked due to atherosclerosis that you'll learn about in your pathology courses. So your body can actually create these bypasses, these natural bypasses around these blocked blood vessels within the heart, and to continue supplying oxygen and nutrients to the myocardium. Blood then that is being supplied to the cardiac tissue by the coronary arteries then has to be returned to the venous circulation. So the cardiac veins then will return that blood from the coronary arteries, and remember that it's going to bring it back to the right side of the heart, to the right atrium, through the coronary sinus. As a summary then, make sure you understand how blood is routed through the heart, that the right side of the heart is going to receive deoxygenated blood into the atrium. Atrium then will shunt blood into the right ventricle through the tricuspid valve, and then from the right ventricle we go through the pulmonary semilunar valve into the pulmonary trunk, and then into the pulmonary arteries that will bring the blood into the lungs. The oxygenated blood will then return via the pulmonary veins into the left atria through the mitral or bicuspid valve into the left ventricle, and then left ventricle will pump the blood up through the aortic semilunar valve and into the aorta and pulmonary circulation. We're going to look now at a little more physiology associated with the heart, and we'll start by looking at cardiac muscle. And recall that there are three different types of muscle in the body. We have skeletal muscle, we have smooth muscle, and there's cardiac muscle. And cardiac muscle has some unique functions or characteristics of its anatomy, and one being that it has these intercalated discs, which are basically gap junctions between the different muscle fibers. So these gap junctions allow a very quick transfer of electrical signals between these branching cardiac muscle fibers, so that once that electrical impulse is generated, it spreads very quickly in all directions from muscle fiber to muscle fiber. So in the heart we have what's known as the atrial and the ventricular syncytium. So what this refers to is that the atria, when there's an electrical signal, both atria are going to contract together at the same time. And so this has to do again with that very quick transfer of electrical signals from left atria to right atria once that electrical impulse is generated through these gap junctions. And then once both atria will contract together and then relax, and then both ventricles will contract together. So these are known as syncytiums or functional syncytiums. There's an atrial syncytium, both atria contract together, and there's a ventricular syncytium, both ventricles contract together. Another unique aspect of cardiac muscle fibers is that there are some fibers that have the ability to create their own action potential, so without the input of a nerve supply. So these fibers have the property of autorhythmicity, or they are autorhythmic muscle fibers. So they are able to generate an electrical impulse on their own, spontaneously, and they're important in setting up the rate at which the heart will beat, as well as creating a pathway for these electrical signals to be transmitted to the atria and also to the ventricles during the cardiac cycle. The sinoatrial node is located in the right atrium. The SA node is considered to be the pacemaker of the heart, and it's the SA node that will establish the rhythm, or the frequency of the action potentials that are generated, the electrical signals that will then be transmitted throughout the myocardium. So the SA node, when it fires, will then send that electrical impulse over to the left atria, and as well as to the another node called the atrioventricular node that's in the interatrial septum, the wall between the two atria. So when the SA node fires, that electrical impulse is sent through the intercalated discs, the gap junctions, very quickly to the left atrium. So both left and right atrium will contract together as a functional syncytium. And this signal that is then sent to the AV node contracts or fires at a slower rate than the SA node. This is why the SA node is the pacemaker of the heart. The AV node there'll be a delay that happens once this electrical impulse is received from the SA node. And then the AV node will fire to send that information into the bundle of His. And the bundle of His is the first part of the pathway that will enter into the interventricular septum, the wall that separates the left and right ventricles. And from here, the bundle of His, or the atrioventricular bundle, will split into left and right bundle branches, left, or this will be the right, left bundle branches. And the bundle branches will then continue into the walls of the ventricles, left and right ventricle, and then we'll further divide into these Purkinje fibers. And it's the Purkinje fibers that will cause the contraction of the ventricle, the myocardium in the ventricles, as well as the contraction of the papillary muscles when these ventricles contract. So both ventricles then will contract at the same time. Right, so SA node fires, electrical impulse is sent to left atrium, so both left and right atrium fire together. There's a slight delay at the AV node receiving that signal, and that allows both atria to contract fully before the signal is sent into the ventricles. And so from the AV node, bundle of His, left and right bundle branches into the Purkinje fibers, and then both ventricles will contract together. Tachycardia versus bradycardia as two definitions. If you have an increase in heart rate, that's known as tachycardia. If you have a decrease in heart rate, that's known as bradycardia. An electrocardiogram, or an ECG, is a way of monitoring the electrical conduction system, or the electrical pathway within the heart during its cardiac cycle. So by placing electrodes over the chest wall, we can pick up those electrical signals as they're being transmitted through the different parts of the heart, and then we can monitor to see how well that's performing. So if somebody has had damage to the heart due to a heart attack, let's say, you may now have an interruption of that electrical pathway. So the current has to take a different direction to get to the ventricles, for example, and that can be reflected in the shape of the ECG when you see it on the graph being mapped out. The series of events that occur then during one cardiac cycle start with the atria. So we know that the SA node fires, and this causes both atria to contract at the same time. So when we have this active phase, it's known as systole, so we're in atrial systole. And then both ventricles will contract at the same time, so then we're in ventricular systole. And then the entire heart will relax for a short period of time, and this is known as diastole. When the ventricles are contracting in systole, there is a passive filling that is occurring at the same time in both atria. So both the atria are also in diastole during this period. We look at this image of the cardiac cycle. We'll start with this side where we have both atria are in systole. So the SA node would have fired, sent that impulse over to the left atria, and now both atria are in systole. They're both contracting at the same time, and that's forcing blood from the right atrium into the right ventricle and forcing blood from the left atrium into the left ventricle. So while both atria are in systole, both ventricles are in diastole, and they're being filled with blood. On this side, we see now that the ventricles are now starting to fire. So we have the SA node here sending an impulse to the AV node. The AV node would then send that electrical impulse down the bundle branches and into the Purkinje fibers in the ventricular walls, and that will cause the myocardium in the ventricles and the papillary muscles to contract. And as these muscles are contracting, it's causing an increasing pressure within the ventricles, and the pressure will shut the atrioventricular valves to prevent blood from flowing back into the atria. And this pressure will build up to the point where it's going to force open the semilunar valves in the aorta and in the pulmonary trunk, and cause the blood to go into the pulmonary trunk and into the aorta. So both ventricles will be in systole at the same time while this is happening, and at the same time both atria are going to be in diastole. So while the ventricles are in systole, there is passive filling of blood going on with both atria. There's blood pouring into the left atria and blood pouring into the right atria passively. So both atria are in diastole while both ventricles are in systole. We'll break the cardiac cycle down into a series of events or periods. The first period we'll look at is during ventricular systole, known as the period of isovolumetric contraction. The word isovolumetric, means the same. So volume will refer to volume. So during this period, both the semilunar valves and the atrioventricular valves are closed. So there's no change in the volume of blood in the ventricles. And the metric component of the word isovolumetric refers to the length of the cardiac fibers. So during this period, the ventricular myocardium is contracting, but the cardiac fibers are not yet shortening. So the isometric means that they're staying the same length at this point. So during this period, there's a building of pressure inside the ventricles. And both the AV valves and the semilunar valves are closed, so there's a building of pressure during the period of isovolumetric contraction within the ventricles. Second part of ventricular systole is known as the period of ejection. So as the ventricles are contracting, the pressure is building inside of the ventricles, and once that pressure is great enough to overcome the pressure that's in the aorta and in the pulmonary trunk, it'll force the semilunar valves to open, and blood is ejected from the ventricles into the pulmonary trunk and into the aorta. Once the ventricles have contracted in systole, they will now go into diastole, and this is known as the period of isovolumetric relaxation. So at this point, the pressure inside the ventricles are dropping very rapidly, and to the point where the pressure that's now in the aorta and in the pulmonary trunk is greater than the pressure in the ventricles. So that allows blood to reflux back from the aorta and pulmonary trunk towards the ventricles. And when this happens, the blood will fill up the cups of the semilunar valves and cause those valves to close. So this is known as the beginning of ventricular diastole, when the ventricles are relaxing. And notice also that the AV valves are still closed at this point. The next period of the cardiac cycle is during diastole again, and this is the passive ventricular filling that's occurring. Remember that when both ventricles were in systole, when they're contracting, both AV valves were closed and the atria were being passively filled with blood. The right atria was receiving blood from the superior and inferior vena cava and the coronary sinus, as well as the left atria receiving blood from the lungs. So once the ventricles have contracted and now are going into diastole, they're relaxing, so the pressure inside the ventricles is dropping, and the atria are filling up with blood at the same time. And once the amount of blood in the atria creates enough pressure to force open the AV valves, now the blood can passively move from the atria into the ventricles and cause a passive filling of the ventricles. So most of the blood that enters the ventricles from the atria is a passive process. Blood just pours in without having to contract the atria. We'll just look at what heart sounds are. Everybody's familiar with the lub-dub that we correlate with the sound of the heart. So this is corresponding to the cardiac cycle. So the first sound, the lub, refers to the sound of the valves, the AV valves that are closing when the ventricles are contracting. So when the ventricles are in systole, it forces the AV valves to shut, and that'll create that lub. And then the second sound, the dup of the lub-dup, occurs as the ventricles relax. And as the pressure inside the ventricles relax, the pressure inside the aorta and the pulmonary trunk will become greater than that within the ventricles, and that'll force the aortic and pulmonary semilunar valves to close. So first sound is the AV valves closing. Second sound is the aortic and pulmonary semilunar valves closing. The active auscultation is using a stethoscope and listening to different parts of the heart and listening for those sounds. You can hear the sounds of the cardiac cycle, the lub-dub, but you can also hear sounds if there is any aberration in blood flow, any turbulence of blood flow, if there's problems with valves that are leaking or are incompetent. So all those different little pathologies will create a different sound that you can auscultate or listen through the chest wall with a stethoscope. This image just illustrates the different points on the chest wall that you can place your stethoscope to best hear the different sounds of the valves, different valves operating. So the tricuspid valve is, you place your stethoscope in this point here to best hear the tricuspid valve, the bicuspid or mitral valve at this point, the pulmonary semilunar valve here, the aortic semilunar valve here. So by listening, you can listen for the lub-dub sounds, but you can also be listening for any whooshing or sounds of the valve not properly closing, or blood is regurgitating back in a direction, in the reverse direction that it should be going. So these are things that you can hear when you're using a stethoscope and auscultating the chest wall. So we talked about the SA node as able to generate its own action potentials, which means that it's going to determine the rate of the cardiac cycle, how often the heart is beating. But the SA node also gets a nerve supply from the central nervous system. So they're both branches of the autonomic nervous system. The sympathetic and parasympathetic branches of the autonomics will innervate the SA node. So even though the SA node doesn't require a nerve supply, so if a heart was removed from the chest cavity during a surgery, it'll continue to beat without a nerve supply. All the nerves have been cut. But there's still within the living person, there's still a nerve connection to the SA node from the central nervous system. So if the sympathetic nervous system is activated during the fight or flight response, the sympathetic nerves will increase the firing rate of the SA nodes. So that you're going to have an increase in the heart rate as well as an increase in the force of contraction of the cardiac muscle. And this is what we want to have happen during this sympathetic response, because we want to increase the amount of blood being pumped by the heart to oxygenate the tissues, the skeletal muscle and the brain that need oxygen and nutrients to deal with this sympathetic response. So it results in an increase in cardiac output. Conversely, if the parasympathetic nervous system is activating the SA node, we know that parasympathetic is involved in the rest and digest state. So this will cause a decrease in the heart rate and decrease in the force of contraction of the heart, because the tissues don't require during rest as much oxygen and nutrients. Two definitions that we need to look at are preload and afterload. Preload refers to the amount of blood or the volume of blood that's going to be returning to the right side of the heart. And with increasing volume of blood coming back to the right side, you're going to get an increased stretch of the walls of the ventricle and the atria on the right side of the heart. And so Starling's law refers to this response that with increasing preload, increasing volume of blood return to the right side of the heart will cause an increase in the strength of contraction of the chamber walls. Afterload refers to the pressure that's in the aorta that the left ventricle has to pump against. So when you take blood pressure of somebody and you put a cuff over their left arm and you're checking their systolic over diastolic pressure, we know that normal is roughly 120 over 80. So the 120 refers to the systolic blood pressure, that's the blood pressure that's in the aorta during ventricular systole, and the 80 refers to the blood pressure that's in the aorta during ventricular diastole. So with increasing blood pressure, let's say if you're at if normal is diastolic pressure is 80, but you have 100 as your diastolic pressure, that means that there's more pressure in the aorta even at rest during diastole that the left ventricle has to pump against to force that aortic semilunar valve open and force the blood into this systemic circulation. So again, preload refers to the volume of blood entering the right side of the heart and the right ventricle. And Starling's law will refer to this preload. With increasing preload, there's an increasing stretch on the ventricular wall, the right side of the heart, and will result in a stronger contraction. Afterload then refers to the pressure that's in the aorta that the left ventricle has to overcome to circulate the blood into the systemic circulation. So generally someone who has ongoing high blood pressure, and especially diastolic pressure that's elevated, this is the pressure that the heart constantly has to work against to try to push the blood into the systemic circulation. So it can be a stressor for the heart. So again, when you're taking blood pressure of somebody, the top number, the systolic pressure, is referring to the aortic pressure, the pressure that's in the aorta during the ventricular systole, ventricular contraction. And the diastolic number will be the pressure in the aorta when the ventricles are in diastole. So 120 over 80 millimeters of mercury is what's considered a normal blood pressure in a healthy young adult, and someone who's older, over 45, 50, 55 years old, pressures can be still considered normal at roughly 140, 145 over 90 millimeters of mercury. We're just going to identify cardiac output or define cardiac output. So this is the amount of blood that's being pumped by the heart each minute. So what you need to know the formula: cardiac output equals stroke volume times heart rate. And you need to know that stroke volume refers to the volume of blood that's pumped from the left ventricle during each cardiac cycle, so during each heartbeat. And the heart rate then will be the number of times your heart will beat per minute. So cardiac output, the amount of blood that's being pumped by the heart each minute, is represented by stroke volume times the heart rate. Baroreceptors are stretch receptors that are found in the aortic arch of the aorta, and also in the carotid sinus of the carotid arteries. So these stretch receptors respond to blood pressure. If there's increasing blood pressure in the arteries, it'll cause these stretch receptors to fire, and this will send a message to the brain stem, central nervous system, that will result in an increase in parasympathetic and a decrease in sympathetic output to the heart, to the SA node, so that the heart rate will decrease its rate, and also cause the blood vessels in the body, the peripheral blood vessels, to vasodilate. So these two effects will result in a decrease in blood pressure. And the opposite will occur if blood pressure is too low. These baroreceptors are not firing, and that's also going to send information to the brain stem to do the opposite. So in this case, now you're going to have a sympathetic response to the SA node to increase the heart rate, and to also result in a constriction, vasoconstriction of peripheral blood vessels to raise blood pressure. So remember, we have to try to keep all parameters in the body within homeostatic ranges, and that includes blood pressure. If blood pressure drops too low, we can go into shock and organs can start to shut down. Or if blood pressure is too high, we need to try to maintain a more normal rate or level. Otherwise, we can, for example, blow a blood vessel in our brain and create an aneurysm or a stroke. We've already talked about the effect of blood pressure on baroreceptors and the baroreceptor response to the heart rate. We also have chemoreceptors, also located in the aortic arch and in the carotid arteries, and the chemoreceptors will respond to the change in pH and levels of carbon dioxide and oxygen within the blood. And so typically what you see is if we're becoming metabolically acidic or respiratory acidosis is occurring because of a increase in carbon dioxide levels in the blood, which results in a decrease in pH, our heart rate is going to increase as a response. We're going to try to circulate the blood more frequently, and that's going to help to oxygenate tissues more effectively with whatever oxygen we are carrying. and also we'll be able to filter the blood more frequently through the kidneys to try to deal with the acidosis that's occurring. We also know that body temperature will affect heart rate, so when you're becoming overheated, your heart rate will increase. So the same idea that if we're circulating the blood more frequently, we're going to be able to get that blood to the surface, shunted to the periphery, where we can lose heat from the blood and try to reduce our core temperature. Conversely, if we're cold, hypothermic, we are going to slow down our heart rate because we're trying to conserve heat, so we want to not circulate the blood as often, and we'll tend to redistribute the blood as well to our core and keep it away from the periphery.